Hello guys, today is the day 4 of second week and we are going strong. This is this is my third day of studying DSA in a row and I feel great, to be honest. I feel like okay, at least I'm being honest with something and I'm working hard for it. So yeah, I don't want to let go of this feeling now. एक minute. Okay, yeah. Wait. Now to be honest, I don't remember मैंने कल कितने पढ़े हाँ मैं कितने क्वेश्चंस मैंने करे हैं, बट आई गेस रिवर्सिंग नोट्स आई गेस मैंने हाउ टू चेक इफ अ लिंक्ड लिस्ट इज अ पैलिंड्रोम किया था, देन एडिंग टू नंबर्स वाला किया था, एंड देन सॉर्टिंग अ लिंक्ड लिस्ट एंड मर्जिंग टू सॉर्टेड लिंक्ड लिस्ट। आई गेस मैंने ये चार करे थे कल, तो अब मैं इनके आगे बढ़ूंगा। Okay, and the time is almost 3 p.m. एंड आज शायद मैं 2 या 2.5 घंटे की स्ट्रीम ही कर पाऊँ। ढाई में ज़्यादा बोल दिया, शायद 2 घंटे की कर पाऊँ मैं, क्योंकि मेरे को शाम में कुछ काम है, मार्केट जाना पड़ेगा मुझे। बट या आई मेक इट काउंट, आई मेक इट काउंट। ओके देन लेट्स स्टार्ट। बाय द वे ये जो क्वेश्चन है, जो लाइक रिटर्निंग द नोड वेयर द साइकिल स्टार्ट्स या वेयर द लूप स्टार्ट्स, दिस इज़ वेरी 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 इजी if you already know how to check a loop वाला प्रॉब्लम। उसमें लाइक बेसिकली वी हैव टू रन टू पॉइंटर्स स्लो एंड फास्ट फ्रॉम द हेड, एंड देन अगर वो लूप में रहेगा तो मतलब ऐसा इंट्यूशन ही कहता है, लाइक वो हिट एंड ट्राई वाला मेथड, एक ऐसा पैटर्न ऑब्जर्व किया था एंड देन इस कंक्लूजन पे आए थे कि स्लो एंड फास्ट जहाँ पे लाइक अगर वो कोइंसाइड कर गए, एक ही नोट पे दोनों आ गए, तो फिर मतलब या देयर इज अ लूप। एंड वहाँ तक ये रहा, देखो ये कोड पूरा वही है। नाउ यहाँ क्या करना है, लाइक इफ़ तो ठीक है, एल्स रिटर्न नन, मतलब कि अगर लूप नहीं है तो फिर कुछ रिटर्न नहीं कर रहा है वो। देन हमको क्या करना है, जो स्लो है उस वाले स्लो को फिर से हेड पे लेके आना है, एंड स्लो और फास्ट को दोनों को एक एक पॉइंट से आगे आगे बढ़ाते रहना है। एंड वही सेम है कि इंटूटिव प्रोसेस है, एंड जिस पॉइंट पे वो कोइंसाइड कर जाएंगे वही रहेगा द पॉइंट वेयर द लूप इज स्टार्टिंग। एंड देन क्योंकि स्लो एंड हेड कोइंसाइड कर गए हैं, तो मतलब दोनों उसी नोट पे हैं, तो हम स्लो रिटर्न कर देंगे, क्योंकि यहाँ पे हमने स्लो को शुरू किया था, मतलब स्लो कंडीशन में स्लो डाला था। ओके हाँ, सो दैट वाज दिस प्रॉब्लम एंड लेट मी सबमिट इट। ओके हाँ, दिस वर्क्स फाइन। एंड मैंने एक चीज़ नोटिस करी है, जो जीरो एम एस वाले सॉल्यूशंस रहते हैं ना, भाई उसमें ये डाल देते हैं वो लोग, एंड देन बेसिकली दे चीट थ्रू द सिस्टम। बट आई एम नॉट गोना डू इट, क्योंकि मैं CPP नहीं कर रहा हूँ, कॉम्पिटिटिव कोडिंग प्रैक्टिस नहीं कर रहा हूँ। या सो हाँ, एंड ये वाला मेरा हो गया। अभी मैं फ्लैटनिंग ऑफ अ लिंक लिस्ट पढ़ रहा था, ये रहा। एंड थोड़ा सा समझ तो नहीं आ रहा है, बट ट्राई कर रहा हूँ समझ के। ये हो जाएगा, देन मेरा ये हो जाएगा। और इसमें अच्छा कुछ क्वेश्चन नहीं है। रिवर्स लिंक लिस्ट इन ग्रुप ऑफ साइज, ये मैंने चालू किया था, लाइक मेरे को समझ नहीं आ रहा था, टू बी ऑनेस्ट। काउंट टोटल नोट्स रिवर्स के ग्रुप्स एट अ टाइम, मतलब एल्गोरिथम समझ आ गया था बट कोडिंग मेरे को समझ नहीं आ पा रहा था. ऑल्सो दिस इज लेबल्ड एज हार्ड, सो यू नो थोड़ा वहाँ पे मेरा कॉन्फिडेंस डगमगा गया, इसलिए मैं इसको थोड़ा ग्रेस नहीं कर पाया था उसमें, तो मैंने इसको स्टार कर दिया था. अ फाइंड इंटरसेक्शन पॉइंट ऑफ वाइल इंग्लिश वाला बचा है, एंड देन मेरा डे 6 पूरा ख़त्म हो जाएगा. रिमूव ये वाला, मैं ये वाला भी कर सकता हूँ, एंड देन ये वाला एक बचेगा, और इसमें तो मैंने कर ही लिए हैं, ये एक बचा है, तो 3 मेरे बचे हैं लिंक लिस्ट के, बाकी फिर शीट में से मेरे लिंक लिस्ट वाले सारे प्रॉब्लम्स ख़त्म हो जाएंगे. एंड देन आई एम थिंकिंग ऑफ बिट मैनिपुलेशन है कि नहीं इसमें. बाइनरी ग्राफ डीपी ट्री, ट्राई ट्राई लिखा हुआ है, कम ऑन. ग्राफ, बाइनरी ट्रीज, बाइनरी सर्च, बाइनरी ट्री, बाइनरी बाइनरी ट्री बहुत बड़ा टॉपिक है क्या. स्ट्रिंग, ये रहा स्ट्रिंग पार्ट 2. आई गेस मैं स्ट्रिंग शुरू कर सकता हूँ इसके बाद. हीप्स, रिकर्शन एंड बैक ट्रैकिंग, रिकर्शन, ग्रीडी एल्गोरिथम, लिंक लिस्ट तो हो गए. बिट मैनिपुलेशन नहीं है इसमें, बट या वट एवर. इसके बाद आई विल डू स्ट्रिंग्स, एंड देन उसके बाद आई विल डू समथिंग, एंड आई एम चूजिंग a race, like आई एम लीविंग a race for the last, क्योंकि थोड़ा सा भाई मतलब डर लगता है रेस को देख के, एंड इसमें इतने ऑलरेडी कितने सवाल हैं, 24 सवाल हैं रेस के. ओके सो या नाउ आई एम गोना म्यूट माय माइक एंड गोना स्टार्ट स्टडिंग. एक ऐसा पैटर्न ऑब्जर्व किया था, एंड देन इस कंक्लूजन पे आए थे कि स्लो एंड फास्ट जहाँ पे लाइक अगर वो कोइंसाइड कर गए, एक ही नोट पे दोनों आ गए, आगे आना है, एंड स्लो और फास्ट को दोनों को एक एक पॉइंट से आगे आगे बढ़ाते रहना है, एंड वही सेम है कि इंटूटिव प्रोसेस है. एंड जिस पॉइंट पे वो मेरे को समझ नहीं आता टू बी ऑनेस्ट, लिस्ट तो हो गए, समझ नहीं आता टू बी ऑनेस्ट. हेलो गाइस, माइक चेक. एंड आई गेस अब गेन ठीक होगा, पता नहीं -17 क्यों था. या लेट मी चेक. हेलो गाइस, माइक चेक. एंड आई गेस अब गेन ठीक होगा, पता नहीं -17 क्यों था. या लेट मी चेक. मेरे को लगता है अब ठीक होगा यार, वो भी कम ही लग रहा था मेरे को, एंड मैं नॉर्मल वॉइस में बोल रहा हूँ. अगर मैं तेज़ बोलूँगा तो इतना तेज़ आ रहा था. लेट मी चेक इट. चेक इट. मेरे को लगता है अब ठीक होगा यार, वो भी कम ही लग रहा था मेरे को। एंड मैं ये नॉर्मल वॉइस में बोल रहा हूँ, अगर मैं तेज़ बोलूँगा तो इतना तेज़ आ रहा था।
Not move the rest because this will help you to get the head back once you have we compared 19 and 28. Now, among this, which one is the smaller one? 19 is the smaller one. So, what we do is we point temp's bottom to the node which is containing 19. Now, remember, you're not creating any new node, you're just pointing it to the same node which is over here. So, you pointed it to 19. Now, right after this, what we do is we just move temp. Now, do not move the rest because rest will help you to get the head back once you have completed forming the entire list will count of 10% given linked list instead of n linked list. Like over here you have 4 linked lists, but just imagine if you had 2 linked lists, then how could you have solved the problem? So for an example, let's take only 2 linked lists to start off with. So let's take the 2 linked lists as linked list 1 as this and linked list 2 as this. Now, if you want to flatten these 2 linked lists, will it not be similar to merging the 2 linked lists into one? Yes, it is kind of similar to merging 2 sorted linked lists into one sorted linked list. So we are going to use the technique that we used in the merge step in the merge short. Now, the first step, what we do is we create a dummy node and we assign it to temporary and rest. Yes, two nodes will be assigned to the dummy node just because we want to keep a track of it. That is why I'm assigning 2 nodes. Now, right after this, what we do is we keep 2 pointers, one at 19 while the other one at 28. Now, if you remember the merge step in the merge shot, what we did is we compared both of them. Yes, we compared 19 and 28. Now, among this, which one is the smaller one? 19 is the smaller one. So, what we do is we point temp's bottom to the node which is containing 19. Now, remember, you're not creating any new node, you're just pointing it to the same node which is over here. So, you pointed it to 19. Now, right after this, what we do is we just move temp. Now, do not move the rest because rest will help you to get the head back once you have completed forming the entire sorted flattened linked list. So temp is over here. Now, since 19 has been taken, move the pointer to the next. So you have 22. Now, it's time to compare 22 and 28. Now, which one is smaller? You can say 22 is smaller. So again, the bottom of 19 will point to the node which is containing 22. Right after that, you will move temp to 22, and since 22 has been taken, you move the pointer to 50. After this, when you compare 50 and 28, 28 is the smaller one. So the bottom will now point to 28. And after that, you'll move temporary to 28. So since 28 has been taken, the pointer will move to 35. So again, comparing 50 and 35, the smaller value that you get is 35. So the bottom of temporary is going to point to 35. So I can say after this, I'll move temporary to 35. Since 35 has been taken, let's move the pointer to 40. Now among 50 and 40, which one is the smaller one? I can say 40 is the smaller one. So let's take 40 and point the bottom of the temporary to 40. And after that, let's move the temporary node. Since 40 has been taken, we move the pointer to 45. Right after this, if I ask you 50 is smaller or 45, the answer is 45. So we point the bottom of temporary to 45. And after that, we're going to move temporary to 45. Now, after this pointer will get exhausted. So that means the linked list 2 is empty. There are no further nodes remaining in linked list 2. So if you remember the merge step in merge sort, what we did is we copy pasted whatever is remaining over here. So only 50 is remaining. So we will copy paste 50 and temporary will now point to 50. Now you remember 50 will be pointing to null and 45 will be pointing to null. So 50 is also going to point to null. So once the two linked lists have been flattened into one, you can say that the bottom pointer of the res, yes, bottom pointer of the res will be pointing to the head of that flattened linked list. Yes, so you can simply point 19's next to null because that is what was required. So how can we use this to solve our original problem? Let's see. So we actually know how to flatten two linked lists into one. So why can't we take the last two linked lists and flatten them into one? So let's flatten. So we actually know how to flatten two linked lists into one. So why can't we take the last two linked lists and flatten them into one? So let's flatten the last two linked lists into one and let's see what we get. So once you flatten the last two linked lists into one, you will have a single linked list instead of the last two. Now again, can I say, let's flatten these two linked lists. What if I flatten these two linked lists? So again, I'll get one more linked list. So let's do that. So now I flatten the other two linked lists into one, and what I get is a single linked list. And at the end, I can see I have two linked lists. Now, what if I flatten these two linked lists into one? The result that I get is going to be the answer that I require. So I can say that the solution to this problem is super simple. What I can do is I can start from the last two linked list, merge them. Once they are merged into one, I can take it and then I can merge it with the third last linked list. Once again they're merged into one, I can merge it with the fourth last linked list, and it can continue till we do not reach the first linked list. And once we have reached the first linked list, I can merge the first linked list and the resultant linked list, and ultimately I'll get the final linked list, which will be my answer. So if you have understood the entire thought process and the logic behind solving this problem, the first thing while coding that will come to your brain is to use recursion. Yes. So what we can do is we can use recursion. So initially, let's start with flatten, and we call L1. And since L1 is not the last node, what we do is we again call flatten, and this time it will go to the next. So the next is L2. So we move to the next. And right after this, what we do is we move to the next, because L2 is also not the last one. So we move to L3. Now L3 is again not the last one. So we move to L4. So we're going to call on recursions. Now, the moment we reach the last node, that's going to be our base case of the recursion. So once you have reached the last node, that's going to be your base case. That is where you stop. And what you're going to do is you're going to return the L4 node. So over here, you have the L4 node. So what you do is, before returning, before going back to this call, let's call a merge function, which will be merge L3 and L4. Now imagine merge of L3 and L4 gives you something as L5. So we get a single linked list in place of two linked lists, L3 and L4, that is L5. And that is what we are going to return from here. That is L5. So we are going to return L5. So over here, again, we are going to call the merge function, but the merge will happen between L2 and L5. So apparently, L3 and L4 would have got a single one, that's L5. So now that L5 will attach with L2 to give something new, that is L6. Yes, so you're going to get L6, and that is what we're going to return from here, L6. So L6 is what we are returning to the function call of L1. So over here, again, we're going to call a merge function, which is going to merge L1 and L6. So when we merge L1 and L6, we get a single linked list, which is this one. So when we merge L1 and L6, we get a single linked list, that is the flattened linked list, which is going to be our answer. So let's talk about the time complexity. Now, since I'm traversing through all the nodes, yes, through all the nodes, so I can say the summation of nodes, the summation of the total number of nodes will be my time complexity. And if I talk about the space complexity is big O of 1, because I'm using the same pointers. Yes, I'm using the same pointers and the same nodes to flatten them into a single linked list. So the space complexity is going to be big O of 1. Now it's time to discuss the C++ as well as the Java solution to this problem. So it's time to discuss the Java code to the approach that we discussed. So let's first discuss the merge step. So imagine you're given, in that case, I will take all the elements of B list, L3 and L4, that is L5. And that is what we are going to return from here. That is L5. So we are going to return L5. So over here, again, we are going to call the merge function, but the merge will happen between L2 and L5. So apparently, L3 and L4 would have got a single one, that's L5. So now that L5 will attach with L2 to give something new, that is L6. Yes, so you're going to get L6, and that is what we're going to return from here, L6. So L6 is what we are returning to the function call of L1. So over here, again, we're going to call a merge function, which is going to merge L1 and L6. So when we merge L1 and L6, we get a single linked list, which is this one. So when we merge L1 and L6, we get a single linked list, that is the flattened linked list, which is going to be our answer. So let's talk about the time complexity. Now, since I'm traversing through all the nodes, yes, through all the nodes, so I can say the summation of nodes, the summation of the total number of nodes will be my time complexity. And if I talk about the space complexity is big O of 1, because I'm using the same pointers. Yes, I'm using the same pointers and the same nodes to flatten them into a single linked list. So the space complexity is going to be big O of 1. Now it's time to discuss the C++ as well as the Hey everyone, welcome back to the channel. I hope you are doing extremely well. So today we will be solving the problem find intersection point of the two given link list. So the problem intersection point of the two given link list. So the problem states you'll be given two heads that will be of two different linked lists. Now your task is to find the node at which the intersection of two linked lists begins. Like for example, if you see this linked list, you can see that the intersection point begins at 8. Now remember one thing, they're not asking you to find the node where the value is same. In that case, 1 would have been the answer. No, they're asking you to find the node where the reference node is the same in both the linked list. Now you can ignore the inputs over here because what you will be given is two heads of the two different linked lists, and you need to find the intersection node, and if there doesn't exist any intersection node, you need to return null. For example, if we look at this linked list 1 and this linked list 2, the intersection node is actually 8. Now, you can see that there are multiple nodes which have same values. Like 1 is 1 over here, then you have a 2 over here, then you have a 2 over here. But what they want is the node which is the intersection point of both the linked list. So if you are in an interview, the first approach that you're going to tell the interviewer will be the extreme brute force. The brute force states that you start with one of the linked list. Let's say you stand at 2 and then check for all the nodes. Like you take 1, then you take 2, then you take 8, then you take 7, then you take 6 and check if both the nodes are same. Remember, both the nodes are same, not the value. So you find no nodes are same. Next time you go to 8 and then again you traverse for 1, 2, 8, 7, 6 and check if the nodes are same. So you find again no nodes are same. Next time you go to 1 and again check for 1, 2, 8, 7, 6 and again you check if the nodes are same. Again you find that no nodes are same. Next time you go to 3 and again check for all the nodes and you find that no nodes are same. Next time when you go to 8, that is the moment you see that when you check for 1, then you check for 2, then you check for this 8. This 8 and the node 8 where you're standing at, both the nodes are same. So you can say that this is the intersection point. Now in the brute force, if you exceeded the second linked list and you did not find any node which is matching with the linked list 1, then you can say that there doesn't exist any intersection point. So since you are moving through all given nodes in linked list 2, for every node in linked list 2, you're traversing for all the nodes in linked list 1. So what I can say is if the length of linked list 1 is m and the length of the linked list 2 is n, I can say that the total complexity will be m cross n of this brute force solution. Obviously, the interviewer will not be happy and he'll ask you to optimize the approach. So the optimized approach will be to use hashing. How can you use hashing? So what you do is at first traverse the linked list 1. So you traverse this node, you traverse this node, you traverse this node, you traverse this node, and you traverse this node. Now remember, don't hash the values. Hash the node address, right? Hash the node address. So you hashed all the nodes of linked list 1. Once you have done that, again iterate for linked list 2. So you iterate for this 2. You do not find that node's address in your hash table. Then you iterate for 8. Then you iterate for 1. Then you iterate for 3. The moment you reach this node 8, you see that this node address would have been stored in the hash table when you are traversing for the linked list 1. So you can say that this node 8 is the node which is the intersection point of both the nodes. Now what is the complexity of this method? Since you're traversing at first the first linked list, I can say it will take you a time complexity of big O of n. Then you're traversing the linked list 2. It's going to take you a time complexity of big O of n. So I can say the total time complexity is big O of n plus m, assuming that the hash table is working in big O of 1. And what's the space complexity? Again, it's going to be big O of n because you're hashing all the nodes of linked list 1. So a lot of people over my Instagram were asking me where do I teach live. So I teach at GFG where I take the entire computer program. The people, the tougher it gets. They'll ask you to optimize it on a normal basis. So I'll be leaving the link in the description below. You can check it out. And if you have any doubts regarding to it, feel free to message me at Instagram. Now the interviewer will not be happy with the extra big O of n space that you're using, and he'll ask you to optimize it. So to optimize that, you need to provide him the best approach. Now there can be two best approach. Let me discuss the first best approach first, and then I can discuss the second best approach. Basically, the first best approach is a bit lengthier to code, while the second best approach is a bit shorter to code, but the time complexity is similar in both the approaches. So let's first discuss the first best optimal approach. So in the optimal approach, what you do is you take a dummy node over here and you take one more dummy node over here. And what you do is you traverse both the dummy nodes simultaneously till both of them reach here. And in doing so, you keep the count of the length of the linked list 1, and you also keep the length of the linked list 2. So what you get is 1, 2, 3, 4, 5. So length of linked list 1 is 5, and the length of linked list 2 is 7. So at first, you find the length of the linked list of both the linked list by 1 is 5, and the length of linked list 2 is 7. The length of the linked list 1, and you also keep the length of the linked list dummy node over here. And what you do is you traverse both the dummy nodes simultaneously till both of them reach here. And in doing so, you keep the count of the length of the linked list 1, and you also keep the length of the linked list 2. So what you get is 1, 2, 3, 4, 5. So length of linked list 1 is 5, and the length of linked list 2 is 7. So at first, you find the length of the linked list of both the linked list by traversing dummy 1 and dummy 2 simultaneously till they do not reach the end. At the next step, what you do is you again put dummy 2 and dummy 1 node at the head of the both of the linked list. And after that, what you do is you find the difference of the length of the longer minus the length of the smaller linked list. So the difference that you find is 2. So what you do is you basically move this dummy 2 linked list, basically the longer linked list dummy node by the difference that is 2. So what I do is I move this by 2 iterations. So our dummy 2 reaches the node 1. Now once our dummy 2 reaches the node 1, that means you have covered the difference that was there. And after that, what you do is you simultaneously move dummy 1 and dummy 2. So at the first iteration, your dummy 1 and dummy 2 will reach the node 2 and 3. At the second iteration, your dummy 1 reaches here and your dummy 2 reaches here. So what you can say is the moment your dummy 1 and dummy 2 collides, right? The moment your dummy 1 and dummy 2 collides, you can say that this is the node which is actually the intersection point of both the linked list, and that is going to be your answer. So the steps were very simple. At first, you find the length of the first linked list and you find the length of the second linked list, and you can do that simultaneously by traveling dummy 1 and dummy 2 nodes. After that, you find the difference of the longest minus the shorter linked list. So whatever difference you get, you take a dummy node and make it stand at the head of the longer linked list. And after that, you move it by a distance 2. And once you have moved it, then you move both the nodes simultaneously. At the moment both the nodes collide, you can say that that is the intersection point of your two linked list. Now, what if there was no intersection point in the two linked list, like this example? So in that case, you would have found the differences 2 only. So your dummy 1 and dummy 2 would have stood over here and over here. So what you would have done is you would have moved this dummy 1 and dummy 2, and ultimately your dummy 1 and dummy 2 would have reached null. And since it was said that when they do not collide, you have to return null. So automatically dummy 1 and dummy 2 becomes null at the equal time. So you return null. So there is no issue even if there is no intersection point. So if I discuss about the time complexity, assume that the linked list 1 is the shorter linked list which is having a length of n, and assume that the linked list 2 is the longer linked list having a length m. So since at the first step you're computing the length of both the links simultaneously, I can say you will take complexity of big O of m because you're doing it simultaneously. After that, you are moving it by a difference of big O of n minus m. So what I can say is I'm moving it by m minus n. And after that, I'm traversing it by a distance of big O of n, that is the length of the shorter linked list. So at the worst case, what I can say is the time complexity of this method is big O of 2m, and space complexity is big O of. So this is the first best optimal approach, but I do not prefer this approach. The sole reason is it requires a lot of stuff. At first, you need to find the length of both of them simultaneously. Then you need to move this dummy node by some difference, and after that you have to again move it simultaneously. So it's going to be a lengthier piece of code, and generally the interviewers will not like you writing a lengthier piece of code, because what they want is concise and crisp piece of code. So now let's discuss the second best optimal method, which will be much shorter and cleaner. So I'll be explaining you the intuition of the algorithm. But before that, I just want to show you the algorithm. So the algorithm is basically you take two dummy nodes. One is the dummy one node and make it stand at the head of the linked list one, and you take one more dummy node, dummy two, and make it stand at the head of the linked list two. And after that, you start moving both of them simultaneously at every iteration. So over here, dummy one will move to here, and after this, dummy two will move to here. So this is the first iteration. And the second iteration, you move the dummy one over here, and the dummy two over here. In the third iteration, you move your dummy one over here, and move your dummy two over here. At the fourth iteration, you move your dummy one over here, and your dummy two over here. At the fifth iteration, your dummy one moves here, and your dummy two moves here. Very important step. The moment any of your nodes, remember this, any of your dummy node reaches the end point of the linked list, what you do is you take the dummy one node, right? Because dummy one was of linked list one, and you assign it to this head, basically the head of the second linked list. And after this, what you do is again start moving them simultaneously. So now dummy one will move to here, and simultaneously your dummy two is going to move here. At the next step, again dummy one will move here, and simultaneously dummy two is going to move to the null. So if you remember, I said the moment any of the dummy node reaches the null, what you're going to do is the dummy node was belonging to linked list two, so you just shift it to the head of the other linked list, that is linked list one. So your dummy two will now go over here. Now there is something to observe. You can see that as of now, your dummy two and dummy one stands at the same node. So your dummy 2 will now go over here. Now the moment dummy 2 is gonna move to the null. So if you remember, I said the moment any of the dummy node reaches the null, what you're gonna do is the dummy node was belonging to linked list 2. So you just shift it to the head of the other linked list, that is linked list 1. So your dummy 2 will now go over here. Now there's something to observe. You can see that as of now, your dummy 2 and dummy 1 stands at the same node before the next iteration. So the next iteration, your dummy 2 will move here, and your dummy 1 is going to move here. And at the next iteration, your dummy 2 is going to move here, and your dummy 1 is going to move here. So the moment both of the nodes collide, what you can say is you found the intersection point of both the linked lists. Now, had there been no intersection, then both the dummy 2 and dummy 1 would have been null at the similar junction. I'll show you an example for that. But before that, I wanted to explain the intuition on why this worked. So if I talk about the intuition, you know one thing, the moment dummy 1 was reaching here, dummy 2 was here. And whenever dummy 1 reached the end, you took that dummy 1 and placed it at the head of the other linked list. Now, what was left? The difference. Yes, this is the difference too. There were two more iterations left before dummy 2 would have reached null. And after that, the moment dummy 2 would have reached null, you would have taken dummy 2 over here. But while dummy 2 would have moved like this and like this, dummy 1 would have also moved till here. So ultimately, they would have been aligned that and placed it at the head of the other linked list. Now, what was left? The difference. Yes, this is the difference too. There were two more iterations left before dummy 2 would have reached null. And after that, the moment dummy 2 would have reached null, you would have taken dummy 2 over here. But while dummy 2 would have moved like this and like this, dummy 1 would have also moved till here. So ultimately, they would have been aligned to same. Basically, I would have covered the difference distance, and ultimately they would have aligned to the same parameter, and after that I could have moved them simultaneously to find this intersection point. Now, why this works is very simple, because initially you started dummy 2 here, dummy 1 here, so this was the difference, and I know the moment dummy 1 would have reached here, the difference would have been this, and at the next time when you travel this distance, ultimately they would have been aligned to the same. So instead of calculating the lengths of both the linked list, then traversing the other dummy node by the difference, I did it in one go. So if I talk about the time complexity, it's again the same, because what we do is two iterations, correct? So the time complexity is we go off 2m, because at the worst case, you might not find iteration, and your dummy one node will be traversing this, and again the entire this. That's a big O of 2m, and the space complexity is big O of 1. Now, why do I prefer to say this approach in the interview? The reason is the code is very, very small and concise. So it's now time to check out the C++ as well as the Java solution to this second best optimal approach. So if you check out the C++ approach, what you're given is basically the first head of the linked list. Interviewer will not be happy and he'll ask you to optimize the approach. So the optimized approach will be to use hashing. How can you use hashing? So what you do is at first traverse the linked list one. So you traverse this node, you traverse this node, you traverse this node, you traverse this node, and you traverse this node. Now remember, don't hash the values. Hash the node address, right? Hash the node address. So you hashed all the nodes of linked list 1. Once you have done that, again iterate for linked list 2. So you iterate for this 2. You do not find that node address in hash table. Iterate for 8, then iterate for 1, then iterate for 3. The moment you reach this node 8, you see that this node address would have been stored in the hash table when you are traversing for the linked list 1. So you can say that this node 8 is the node which one node will be traversing this and again the entire this. That's a big O of 2m, and the space complexity is big O of 1. Now, why do I prefer to say this? This approach in the interview. The reason is the code is very, very small and concise. So it's now time to check out the C++ as well as the Java solution to this